We begin with counterfactual thinking and potential outcomes, then study randomized experiments, matching, and natural experiments. The natural experiment section develops difference in differences, instrumental variables, and regression discontinuity before comparing the designs and extending them. Causal claims compare the world we observe with a counterfactual world. If I say coffee caused poor sleep, I compare sleeping after coffee with sleeping without it. But for one person at one time, only one state can occur. The missing alternative is the fundamental problem of causal inference. Every design in this chapter is therefore a strategy for learning about an unobserved potential outcome from other observations and credible assumptions. Our goals are to define treatment effects with potential outcomes, diagnose selection bias, analyze randomized experiments, use matching, difference in differences, instrumental variables, and regression discontinuity, and implement the main procedures in R and Python. The class size example shows why association is not enough. A simple regression suggests that more students per teacher are associated with higher scores. That does not mean larger classes improve learning. Swedish schools serving less advantaged children receive extra resources and therefore have smaller classes, while the same background factors also predict lower scores. Socioeconomic background is a confounder. Once parental education is controlled, the estimated slope falls sharply. The causal question requires the assignment mechanism, not merely the correlation. A directed acyclic graph makes the assumed causal structure visible. Here, socioeconomic background points to both class size and test score, while class size also points to the score. The path through background creates confounding. Controlling for the common cause blocks that backdoor path under the assumption that the graph is correct and the confounder is measured well. The arrows are not estimated by the picture. They record substantive assumptions that guide the regression design. Variables play different roles. A confounder affects both treatment and outcome and should be controlled. A variable affecting treatment only can raise variance without removing bias. A variable affecting only the outcome can improve precision. A mediator lies on the path from treatment to outcome. Controlling for it removes part of the total effect. The practical rule is to choose controls before treatment occurs. Post-treatment variables can create bias rather than solve it. For a binary treatment, each individual has two potential outcomes, one under treatment and one without it. Their difference is the individual causal effect. We observe only the outcome corresponding to the treatment actually received. The other remains missing. Treatment assignment can itself be regarded as random. This notation separates the causal quantities which conceptually exist for each person from the observed data, which reveal at most one of them. There are two inferential perspectives. Design-based inference treats the sample's potential outcomes as fixed and uses randomness from assignment. Model-based population inference treats individuals as sampled from a larger population. The average treatment effect averages the individual contrast over the population. The average effect on the treated conditions on receiving treatment. These estimands can differ when effects vary across people, so every study must state the population and contrast it intends to learn about. The table distinguishes three common estimands. The average treatment effect covers the full population and can be identified by a randomized experiment or, under stronger assumptions, matching. The average treatment effect on the treated concerns those who actually receive treatment and is common in matching and difference in differences. Instrumental variables generally identify a local average treatment effect for compliers. These are not interchangeable numbers. The relevant one depends on the policy question and the design. The stable unit treatment value assumption has two parts. No interference means one person's potential outcome does not depend on another person's treatment. No hidden versions means treatment is well defined. Vaccination illustrates a violation. Treating one person can reduce infection risk for others. When interference exists, the simple notation with one treatment indicator per person is incomplete, and a difference in means may combine direct and spillover effects. State the treatment and exposure structure carefully. A raw treated control comparison mixes two pieces. One is the causal effect on the treated. The other is selection bias. Treated and untreated units may have different untreated potential outcomes before treatment begins. Evening coffee drinkers, for example, may drink coffee precisely because they otherwise sleep well, or because their schedules differ. The observed difference cannot reveal the causal effect unless the baseline difference is removed by design or made negligible under credible assumptions. Random assignment makes treatment independent of both potential outcomes. The treated and control groups then have the same expected untreated outcome, so selection bias disappears. The difference in their average observed outcomes estimates the average treatment effect. Randomization is powerful because it controls observed and unobserved confounders in expectation without modeling them. Its credibility still depends on implementation. Assignment must truly be random, and later attrition or non-compliance can disturb the comparison. With treated and control groups, the experimental estimator is the difference in sample means. It is unbiased for the sample average treatment effect under the randomization. A conservative variance estimate adds the group-specific outcome variances divided by their sample sizes. The same result is obtained by regressing the outcome on the treatment indicator with heteroscedasticity, robust standard errors. Pre-treatment covariates may improve precision, but they are not needed to repair confounding created after random assignment. In a small experiment, normal approximations may be unreliable. Fisher's randomization test evaluates the sharp null of no effect for anyone. Under that null, every missing potential outcome is known, so we can enumerate or simulate all treatment assignments allowed by the design and compare their statistics with the observed one. The resulting p-value is exact under the assignment mechanism and requires no outcome distribution. Notice that the sharp null is stronger than a zero average effect. Human experiments face practical complications. Some assigned to treatment do not receive it. Participants may leave the study selectively. Behavior can change because people know they are observed, and ethical limits may rule out randomization. For non-compliance, the standard policy estimand is intention to treat, the effect of assignment regardless of uptake. With a valid assignment instrument, one may also estimate the local effect among compliers. Never silently replace assignment by actual receipt and call the comparison randomized. Rubin's causal model for observational data tries to mimic an experiment by modeling treatment assignment. Unconfoundedness says potential outcomes are independent of treatment after conditioning on observed pre-treatment covariates. Overlap says every covariate profile has a positive probability of receiving either treatment. Together, they make treatment as good as random within covariate strata. They are strong assumptions. Unobserved confounders remain a threat, and poor overlap means some units lack credible comparisons. The propensity score is the treatment probability given observed covariates. If unconfoundedness holds for the full covariate vector, conditioning on the scalar score is sufficient. Estimate it, match each treated unit to a control with a similar score, and then inspect covariate balance. Balance, not predictive accuracy, is the diagnostic goal. If important covariates remain different, revise the score model or discard poor matches. Only after balance is satisfactory should the treatment effect be estimated. After matching, estimate the effect on the treated by averaging each treated outcome minus its matched control outcome. A simple difference in means or a regression adjustment can then be used with appropriate uncertainty for the matching procedure. The caveat is central. Unlike random assignment, matching controls only observed confounders. A well-balanced matched sample can still be biased if an important common cause was unmeasured. Matching improves comparability. It does not manufacture experimental evidence. The cognitive behavioral therapy study asks whether treatment reduces sickness absence. The Swedish data include roughly 14,700 treated individuals and nearly 170,000 controls. Before matching, the treated group is younger, better educated, and healthier. The analysis estimates propensity scores from more than 20 pre-treatment covariates and matches comparable individuals. The design succeeds only if those variables capture the relevant selection process and the matched groups achieve balance. The key findings differ by baseline status. Among people not on sick leave when therapy began, treatment is associated with significant reductions in sick leave and prescriptions. Among those already on leave, there is no significant long-run effect. Placebo analyses show no pre-treatment effects, supporting the design. This heterogeneity matters. An average across both groups could hide different treatment responses, and matching estimates apply to the treated people who found credible comparisons. The 6 panels show effect paths around treatment for several sickness absence and prescription outcomes. The vertical line marks the intervention. Pre-treatment estimates are generally near zero, while some outcomes move after treatment and others do not show a lasting change. Read the confidence bands as well as the central lines. The figure supports the verbal conclusion on the previous page and illustrates why a dynamic plot can reveal timing and pre-trend evidence that one average coefficient would conceal. Pre-analysis plans separate design from outcome-driven searching. Researchers who try many specifications and report only significant results create false positives. A plan written before outcome data are examined specifies outcomes, estimates, covariates, and analysis choices in advance. It makes the process transparent and limits selective reporting. This logic fits matching particularly well. Treatment assignment and balance can be designed without using outcomes. Exploratory analyses remain valuable, but they should be labeled as exploratory rather than presented as pre-specified confirmation. Natural experiments exploit treatment variation generated by rules, geography, weather, timing, or other forces beyond individual control. The researcher does not create the assignment, so credibility rests on arguing that the resulting variation is exogenous for the comparison of interest. The methods developed here are difference in differences, instrumental variables, and regression discontinuity. Each uses a different source of quasi-random variation and identifies a different population effect. None is credible by method name alone. Difference in differences compares two groups over at least 2 periods. The treated group experiences an intervention in the later period. The control group does not. Neither is treated initially, and assignment need not be random. The method subtracts the control group's change from the treated group's change. John Snow's cholera study is an early example. The design removes permanent group differences and common time shocks, but it relies on a credible counterfactual trend. Snow's idea was that cholera spread through contaminated drinking water. One company later moved its intake upriver, away from much of the sewage, while the other continued drawing water from the more polluted section of the Thames. That change created the natural comparison developed on the next page. The difference in differences logic takes the mortality change for customers of the company that moved upriver and subtracts the change for customers of the company that did not. If background time forces affected both groups similarly, the remaining difference is attributed to cleaner water. Supplier assignment was not literally randomized, so socioeconomic and demographic composition could differ. The design removes fixed differences, but not a separate trend or concurrent shock that changes only one group. The schematic shows observed and counterfactual outcomes. Before treatment, the groups differ in level. After treatment, the control group's change is used to project what would have happened to the treated group without the intervention. The treatment effect is the gap between the treated outcome and that projected counterfactual. The method does not require equal levels. It requires parallel untreated trends. Absent treatment, the difference between groups would have remained stable over time. The regression includes a treatment group indicator, a post-period indicator, and their interaction. The intercept is the control group's pre-period mean. The group coefficient is the initial difference, the time coefficient is the common change, and the interaction is the difference in differences effect. With many groups or repeated observations, standard errors should be clustered at the assignment level. The number of independent clusters, not the number of rows, drives the relevant asymptotic approximation. Parallel trends is the key assumption. The red and blue solid lines in the figure rise at different rates even before treatment, while the dashed counterfactual incorrectly imposes the control trend on the treated group. That creates an apparent effect where none exists. Pre-treatment data cannot prove what would have happened later, but similar earlier trends make the assumption more plausible. Diverging pre-trends are a strong warning against the design. With several pre-treatment periods, plot the outcome paths and estimate placebo effects before treatment. The childbirth example shows men's and women's income moving similarly beforehand, then women's income falling sharply relative to men's after childbirth. That pattern supports the difference in differences interpretation. A placebo regression using only pre-period outcomes should find no spurious treatment effect. Evidence of anticipation or divergence before the event would weaken the design. The figure traces income for men and women around childbirth. The trajectories are close before the event and separate sharply afterward, with women's income dropping and only partly recovering. The pre-event fit supports the common trend assumption, while the post-event gap reveals a persistent child penalty. The plot also makes effect dynamics visible. The impact is not a single constant jump. Confidence in the interpretation still depends on no other event changing the groups differently at the same time. The R code fits the interaction model with cluster-robust standard errors at the group level. The treatment indicator marks the exposed group, the post indicator marks the later period, and their product is the causal coefficient under parallel trends. Clustering accounts for correlated outcomes within assignment groups over time. The code is short because the design work occurred before estimation, defining treatment, timing, comparison units, and the level at which shocks may be shared. Instrumental variables address an endogenous treatment where omitted confounding, reverse causality, or measurement error makes the treatment correlated with the regression disturbance. An instrument shifts treatment but does not directly affect the outcome. It isolates variation in treatment that is plausibly unrelated to the unobserved determinants of the outcome. The statistical machinery is straightforward. The hard part is defending why the instrument changes the outcome only through treatment and is itself exogenous. A valid instrument must satisfy three conditions. Relevance means it predicts treatment. Exclusion means it affects the outcome only through treatment. Exogeneity means it is unrelated to the unobserved determinants of the outcome. Relevance can be examined in the first stage regression. Exclusion and exogeneity are design assumptions that require substantive arguments and falsification checks. They cannot be certified by a large first-stage statistic. A strong but invalid instrument produces a precise answer to the wrong question. The letter increased the quitting rate from 20 to 43%, a difference of 23 percentage points. Children of mothers who received the letter were about 98 grams heavier at birth. Scaling that birth weight gain by the increase in quitting gives roughly 426 grams. Expressed as the effect of smoking rather than quitting, the sign is negative. Smoking lowers birth weight by about 426 grams for compliers. Three equations organize instrumental variables. The structural equation contains the causal treatment effect, but has endogenous treatment. The first stage measures how the instrument changes treatment. The reduced form measures how the instrument changes the outcome. With one valid instrument, the causal estimate is the reduced form effect divided by the first stage effect. That ratio is meaningful because exogeneity removes confounding of the instrument and exclusion channels its effect through treatment. Two-stage least squares generalizes the ratio to several instruments and controls. First, regress treatment on all instruments and exogenous controls and obtain fitted treatment. Second, regress the outcome on fitted treatment and the same controls. The fitted slope is the instrumental variable's estimate. Do not calculate ordinary second-stage standard errors by hand. They ignore that fitted treatment was estimated. Use dedicated software which provides the correct covariance matrix and first-stage diagnostics. A weak instrument changes treatment only slightly. In finite samples, the two-stage estimate is then biased toward ordinary least squares, and its standard errors are unreliable. The first-stage statistic is a diagnostic. A value above 10 is only a common screening rule, and with many instruments, much stronger evidence may be needed. Always report the first stage, but do not confuse strength with validity. An instrument can be strong, excluded by the model, and still violate the causal design. With heterogeneous effects, instrumental variables identify the local average treatment effect for compliers, people whose treatment follows the instrument. Always takers receive treatment regardless of assignment. Never takers never receive it, and defiers move in the opposite direction. Monotonicity rules out defiers. Under the remaining assumptions, two-stage least squares averages effects among compliers, not the full population. The resulting policy interpretation must therefore name the instrument and the behavior it induces. In R, the instrumental variables formula places the structural regressors to the left of the separator and the instruments plus exogenous controls to the right. Diagnostics report first-stage strength and related tests. With multiple endogenous variables or instruments, list the exogenous controls on both sides as required by the interface. The dedicated fitting function corrects the standard errors automatically. Code cannot validate the exclusion restriction. That argument belongs in the research design. The Python implementation explicitly separates the dependent variable, exogenous controls, endogenous treatment, and instruments. Robust covariance is requested at estimation, and the fitted object reports first-stage diagnostics. This structure helps prevent a common specification error, omitting an exogenous control from the instrument set. As in R, a clean summary is only the final calculation. Credibility comes from the assignment story, instrument strength, and evidence against alternative pathways to the outcome. Regression discontinuity uses a running variable and a known threshold that changes treatment assignment. In a sharp design, crossing the cutoff determines treatment. In a fuzzy design, it changes treatment probability without perfect compliance. Units just below and above the threshold should be comparable, so assignment is locally as good as random if they cannot precisely manipulate the running variable. The effect is identified by a jump in the conditional mean at the cutoff. The two panels distinguish the designs visually. In a sharp discontinuity, treatment probability jumps from 0 to 1 at the threshold. In a fuzzy discontinuity, it rises discontinuously but remains between 0 and 1 because some units do not follow assignment. The first estimates a local effect directly from the outcome jump. The second uses cutoff assignment as an instrument for treatment and divides the outcome jump by the treatment probability jump. For a sharp design, continuity of both untreated and treated potential outcome functions at the cutoff implies that the observed jump identifies the local average effect at that threshold. Sorting is the main threat. If individuals can manipulate the running variable to cross the cutoff, units on the two sides may no longer be comparable. Grade inflation just above an admissions threshold is an example. Density and covariate checks help detect such failures. The graph shows the sharp estimate. Fit the relationship between outcome and running variable separately on each side of the cutoff. Extrapolate each local fit to the threshold and measure the vertical gap. The slopes may differ, but the treatment effect is the difference between the two intercepts at the boundary. Observations far from the cutoff should not determine this local comparison, which is why bandwidth choice matters. Within a chosen bandwidth, estimate separate local linear functions on either side. A small bandwidth reduces approximation bias but uses fewer observations and raises uncertainty. A large bandwidth improves precision but risks a poor local approximation. Data-driven selectors and robustness checks help, yet no one bandwidth removes the trade-off. Report the chosen window, local polynomial order, kernel, and sensitivity of the result to nearby choices. A fuzzy discontinuity is an instrumental variable's design near the cutoff. Define assignment by whether the running variable crosses the threshold and use it as an instrument for actual treatment. The reduced form is the jump in outcome. The first stage is the jump in treatment probability. Their ratio is the two-stage estimate. Under continuity, exclusion, and monotonicity, it identifies the local average treatment effect for compliers near the cutoff. The Swedish class size rule provides the chapter's applied discontinuity example. A grade may contain at most 30 students per class, so total enrollment thresholds at 30, 60, 90, and later multiples trigger creation of another class and a sharp drop in average class size. Families cannot precisely control total grade enrollment, limiting sorting. The study finds that chance assignment to smaller classes improves long-run outcomes, including earnings and health. The graph shows the first stage created by the rule. On either side of a normalized enrollment breakpoint, average class size rises with the number of pupils. At the cutoff, it drops sharply because a new class is formed. Separate local fits make the discontinuity visible. That jump supplies exogenous variation in class size. The outcome analysis then asks whether test scores and later outcomes also change at the same threshold. The two panels report long-term outcome discontinuities. Cognitive ability at age 13 and salary later in adulthood are plotted against normalized grade enrollment. The fitted lines change at the same threshold that alters class size. Read the graphs locally. The relevant comparison is among grades just below and just above the breakpoint, not between small and large schools across the full range. The estimates, therefore, concern students near the enrollment thresholds. A credible discontinuity study checks 4 things. The running variable density should not bunch at the cutoff. Pre-treatment covariates should not jump. Placebo cutoffs should show no effect where treatment does not change. Estimates should remain reasonably stable across defensible bandwidths. Passing these checks does not prove the identifying assumptions, but it addresses major threats. When the assignment rule and diagnostics are convincing, regression discontinuity can provide unusually credible quasi-experimental evidence. The R implementation fits the sharp discontinuity with the outcome, running variable, and cutoff. The companion plot adds confidence intervals, while a density test examines manipulation around the threshold. The package uses local polynomial methods and offers bandwidth selectors and bias-aware inference. Defaults are a starting point. A complete analysis reports the selected bandwidth, kernel, polynomial order, and robustness to alternative choices, together with the substantive reason the cutoff is exogenous. The Python page shows the local linear calculation by hand. Restrict the sample to the bandwidth, create a treatment indicator for crossing the cutoff, center the running variable, and interact the indicator with the centered variable so slopes can differ. The treatment coefficient is the jump at the cutoff with heteroscedasticity, robust covariance. For optimal bandwidth and robust inference, a dedicated discontinuity package is preferable, but this regression makes the estimate transparent. The methods differ in assumptions and estimands. Experiments identify an average effect through random assignment. Matching relies on observed unconfoundedness and often targets the treated. Difference in differences uses parallel trends. Instrumental variables require relevance and exclusion and identify compliers. Sharp discontinuity identifies a local effect at the cutoff. Fuzzy discontinuity identifies local compliers. Comparing estimates without acknowledging these populations can create apparent disagreements that are simply differences in what was identified. There is no universal ranking based only on method labels. Ask whether randomization was implemented, important matching confounders were measured, parallel pre-trends are credible, the instrument is strong and excluded, monotonicity is plausible, or the running variable can be manipulated. A technically sophisticated estimator cannot rescue an implausible design. Credibility depends on how well the assumptions fit the institutional setting and on diagnostics tailored to the chosen source of variation. Use an experiment when treatment can be assigned. Use matching when all relevant confounders are observed and overlap is good. Use difference in differences when treated, and comparison groups have credible common untreated trends over time. These designs identify different averages. Experiments often target the population average, while matching and difference in differences commonly target treated units. Choose the design to match both the available variation and the policy population of interest. Use instrumental variables when an exogenous variable shifts treatment but has no direct outcome pathway. The estimate applies to compliers. Use sharp regression discontinuity when crossing a threshold fully determines treatment and sorting is absent. Use fuzzy discontinuity when the threshold changes treatment probability, but not perfectly. The cutoff becomes the instrument. Prefer experiments where feasible. Otherwise, choose the quasi-experiment whose key assumptions are most plausible in context, not the one with the most attractive estimate. Internal validity asks whether the causal estimate is correct for the population actually studied. A well-run experiment is strong on this dimension. A discontinuity can be highly credible for units near its threshold. An instrumental variable's design can be internally valid for its compliers. These statements are conditional on the design assumptions. Internal validity does not tell us whether the same effect would hold in another population, place, or range of the running variable. External validity asks how far the result can travel. A discontinuity estimate concerns units near a threshold, not necessarily the full population. An instrumental variable's estimate concerns compliers induced by that instrument. A difference in differences estimate depends on the group's period and policy setting. Before generalizing, ask who generated the identifying variation and how treatment effects might vary. A narrow but credible local effect can be more useful than a broad claim unsupported by the design. Common errors have a common theme, confusing a convenient regression with a credible design. Do not control for mediators, omit confounders, rely on weak instruments, accept difference in differences without checking pre-trends, fit high-order global polynomials around a cutoff, search until significance appears, or confuse internal with external validity. Each mistake changes either the estimand or the comparison group. Write the causal question and assignment mechanism before choosing the regression. Attrition after randomization can create selection bias if it differs by treatment status. Random attrition mainly reduces precision. Differential attrition changes comparability. Report bounds or sensitivity analyses and check baseline balance among those observed. Non-compliance means assigned and received treatment differ. Intention to treat preserves the randomized comparison. Under instrumental variable assumptions, dividing that assignment effect by the compliance first stage identifies the local effect among compliers. Interference violates the assumption that one unit's outcome depends only on its own treatment. Vaccination can protect untreated neighbours. Classroom interventions can affect peers, and labour market programmes can change wages for everyone. A partial equilibrium estimate may then miss program-wide effects. The remedy is not a routine control variable. Define exposure at the appropriate network, group, or market level, and be explicit about whether the target is direct, spillover, or total policy impact. Modern difference in differences often has staggered adoption, with units beginning treatment at different times. Conventional two-way fixed effects can combine comparisons in ways that do not recover a meaningful weighted average when treatment effects vary across cohorts or time. Newer estimators construct cohort and time-specific comparisons more carefully. The lesson is not that the original design disappears, but that the comparison set must remain valid when timing becomes heterogeneous. An event study interacts treatment with indicators for time relative to adoption. Pre-treatment coefficients assess whether treated and control groups moved similarly before the event. Post-treatment coefficients trace how effects evolve. A flat pre-period supports, but does not prove, parallel trends. Anticipation can appear as movement before adoption. Plot the estimates with uncertainty and state the omitted reference period, because the entire path is interpreted relative to that baseline. Synthetic control is useful when only one or a few units are treated. It builds a weighted combination of untreated units whose pre-treatment outcome path closely matches the treated unit. That weighted series becomes the counterfactual after treatment. The method is a structured alternative to choosing one comparison unit. It is most persuasive when the pre-period fit is strong and no donor unit is affected by the treatment or related spillovers. Choose non-negative donor weights that sum to 1 and minimize pre-treatment mismatch. After treatment, subtract the synthetic outcome from the treated outcome. For inference, repeat the procedure as a placebo for each control unit and ask whether the treated gap is unusually large. The classic application studies a tobacco control policy in California. As with other designs, a dramatic post-treatment gap is credible only when the synthetic control tracks the treated unit well beforehand. Bandwidth selection in discontinuity balances bias from a wide window against variance from a narrow one. Modern selectors automate parts of that choice, but researchers should still report sensitivity. Local linear regression is the standard polynomial order. Higher-order global polynomials near a cutoff can swing wildly because distant observations and outliers determine the extrapolation. Fit locally on each side and let the bandwidth, not a very high polynomial degree, control flexibility. Robustness checks for any discontinuity paper include a density test for manipulation, placebo cutoffs where treatment does not change, a donut specification dropping observations extremely close to the threshold, and checks that predetermined covariates are continuous. Each addresses a different threat. Agreement across them strengthens the design. Failure should change the interpretation or the sample. It should not be hidden behind the main estimate. The first summary returns to the foundations. Potential outcomes define treated and untreated states, but only one is observed. Average treatment effects aggregate the missing individual contrasts. Selection bias arises when treated and control units differ in their untreated outcomes. Random assignment removes that bias in expectation and identifies an average effect. Every observational method that follows tries to recreate a credible counterfactual comparison using additional assumptions. The second summary maps assumptions to estimands. Matching controls observed confounders and often estimates the effect on treated units. Difference in differences uses parallel trends. Instrumental variables use exogenous treatment variation and identify compliers. Sharp discontinuity uses deterministic cutoff assignment and identifies a local effect. Fuzzy discontinuity uses the cutoff as an instrument and identifies local compliers. A causal estimate is always an assumption, a design, and a population, not just a coefficient. Use the final questions to explain why randomization handles confounders, how to interpret the difference in differences coefficients, why a first-stage statistic of 3 is weak, what density bunching threatens, and which data and assumptions a job training evaluation would need under each design.